This video will look at Mendelian inheritance patterns, focusing on a dihybrid cross. First, we'll start out with, what is a dihybrid cross? A dihybrid cross is whenever you're following two different characters at the same time. So it's a similar setup as a monohybrid cross. However, now you're looking at two characters, right? Let's say the first character you're looking at is flower color, but now you're also tracing a second character such as pod color. This resulted in Mendel's law of independent assortment. Here you can see the overall dihybrid cross results that you would expect to find in the F2 generation. So 9/16 dominant for the first trait, dominant for the second, 3/16 dominant for the first trait, recessive for the second trait, 3/16 recessive for the first trait, dominant for the second trait, 1/16 recessive for the first trait, and recessive for the second trait. Right? For our class, we're not going to actually do a dihybrid cross. We'll stick to monohybrid crosses. However, I do expect that a dihybrid cross is looking at two different characters and that you could follow like an example of, well, that would be like breeding this with this. If you're curious though, I will post an example online that you can see a dihybrid cross. Instead of doing like your classic monohybrid 4-square Punnett square, you would be doing like a really giant 16-square Punnett square. But for the purposes of this class, I don't care that you're able to fill in all of these squares, but more just have a basic understanding of what do we mean by dihybrid. More importantly, though, is what do we mean by Mendel's law of independent assortment? And what that is saying is when we're looking at the homologous pairs during cell reproduction, whenever they are lining up and dividing throughout meiosis, we can see that the two separate homologous pairs here, so we have one here and one pair here, represented by the A genes or the B genes, we can see that these pairs are not tied to each other. So these genes, the A gene is not tied to the B gene, right? So we can see that as they separate out throughout meiosis, right, they could have ended up in this way here, a mixture of the big A with the big B's and then the little a with the little b's. But it didn't have to be that way, right? So we can see this one scenario, all the dominant alleles, big A and big B's, lined up on the left, and all the recessive alleles lined up on the right. But it could have been this way, where the dominant big A alleles lined up on the left, and the recessive little b alleles lined up on the left. And that would have completely changed the combination of A's and B's that we would have got down here in the gametes at the end of meiosis. So again, this is saying that these allele pairs from these homologous pairs, they're able to segregate or assort independently of other allele pairs, meaning the inheritance of one color, let's say that the A theoretical gene was coding for flower color that Mendel was looking at, has no effect on the B gene, which may be coding for a separate character such as pod color. So they're not linked to each other. They can align and separate independently of one another.